Let's go back to the idea that the radius of curvature for a charged particle moving in a magnetic field depends on the mass times the velocity divided by the charge times the magnetic field. This leads to a very important application that we call mass spectroscopy. Again, the radius of curvature is mass times velocity divided by the charge times the magnetic field. In a mass spectrometer, what we try to do is keep everything constant except for what we're trying to measure. So we keep the magnetic field constant, we keep the charge of each particle constant. Usually what we're going to use here is a singly ionized ion, okay? We'll keep the mass constant, and again, our experimental value that we're trying to measure is the mass. Mass spectrometers, as their name implies, tries to sort different ions according to how much mass they have. This is very important for determining what isotopes are present. We're well aware of the isotope carbon-14. Carbon-14 is very, very important because it has a half-life of about 5,300 years, which means that every half-life, half of carbon-14 disappears. Now, when something is alive, okay, it is constantly taking in carbon. If it's a living organism, either as a plant, it's taking carbon dioxide and using photosynthesis to generate hydrocarbons, carbohydrates, or if it's an animal, it's eating plants or other animals which contain the carbon-14. Carbon-14 is naturally created in the atmosphere by cosmic rays hitting nitrogen-14 and transmuting it through a decay process to eventually reach carbon-14. So the carbon-14 is always decaying, but it's also being regenerated at the same rate. So all living beings should have the same ratio of carbon-14 to carbon-12. When something dies, however, obviously it's not taking in any more carbon-14. So after one half-life, it's lost half the carbon-14 that it originally started with. So we can tell if something is 5,300 and some years old, okay, if it has half the carbon-14 of what the current carbon-14 concentration is. Okay? Go 2 half-lives, about 10,000 years, it'll have a quarter. Go to, another half-life, about 1,500 years, it'll be down to about an eighth of its original carbon-14 amount. So mass spectrometers are very, very important for separating isotopes or detecting what isotopes are present for carbon dating. A mass spectrometer is really, really essential. So how does this work? How does a mass spectrometer take a sample and analyze it? Well, the first thing we have to do is actually destroy the material. So we try to take a small sample, we'll ionize it, we'll use electrodes to essentially heat it up into a plasma, knock some of the electrons off, and the positive ions are attracted by an electric potential and slowly accelerated. We then send it through what's called a velocity selector. Remember, we want all the ions to be traveling at the same speed. How do we get that to happen? Well, basically, the velocity selector uses a magnetic field and an electric field to produce opposing forces. If we balance perfectly the magnetic force, which is QVB, don't have to worry about sine theta here because we're dealing with perpendicular vectors. If we match that with our electric field, which is QE, the velocity of the particles, which are undeflected, will be equal to the electric field divided by the magnetic field. So we can actually change either the magnetic field or the electric field to only get particles that are traveling at a very specific v, okay? Very specific velocity. So again, we basically turn the sample into a plasma, we accelerate the particles, pass them through this velocity selector, And now here's where we're going to look at their trajectories to try to figure out what their mass is. Okay? So after going through this velocity selector, we have a beam of ions of different mass, but they're all traveling at the same velocity. The radius of their trajectory will go by mv divided by qb. Now, this was the magnetic field in the velocity selector, B. The new magnetic field we'll call B naught. All right? So actually R should be equal to mv over q B naught. If it's a more massive particle, the radius is going to be larger due to larger mass. Again, V is the same for all the particles. Every particle is singly ionized. Every particle is experiencing the same magnetic field. So more massive, it'll travel over a bigger radius. Less massive, a smaller radius. So the detectors will be set up such that they'll be positioned, usually in an array of detectors. At a smaller radius, you'll see carbon 12. A little bit further, you'll see carbon 13. And then a little bit further out, you'll see carbon 14. And you can measure the ratio between the carbon 14 and the carbon 12. And again, get an exact date as to how old that sample is. Okay? We also use this for determining the dates of rocks. Potassium, I believe it's potassium 40. Don't quote me on this. Some of the decay products of uranium and thorium also have very long half-lives. You can determine how old that particular rock is based on the ratio of isotopes. So it's a very important method using some of the very simple principles that we've talked about here. With this mass spectrometer, again, we use the velocity selector to have a beam of only particles traveling at one velocity. They pass through this magnetic field. They're deflected at different angles. And again, depending on what is the heaviest and what is the lightest of the isotopes, we can measure the frequency of each and get a nice ratio there.